Hello dear students, and welcome to this short lecture on what is optimization and how do we use it. Essentially, I want to define what I mean with the title of the course, Applied Numerical Optimization. When an engineer in a daily life talks about optimization, they typically mean improving an existing solution or finding a new solution, which hopefully is good, by some creative, intuitive, brute force method. They go to the lab and they turn some valves, they go to the design board and they think of a new idea. When we talk about optimization, we really mean numerical or mathematical optimization. What we mean is we take a mathematical formulation. We take our system, we model it, we define rigorously what we want to optimize, and then we use a numerical solver to do that. This numerical solver may be rigorous or may be heuristic. Nevertheless, it's a numerical solver. And this is what we're going to be talking about in this course. Another term for numerical or mathematical optimization is mathematical programming. This was the traditional way of describing numerical optimization. Lately, people do not use it so much anymore, and I think this is good because programming to most people is associated with writing a computer program in Fortran or Python or C++. The term mathematical programming has a different meaning. So programming is not in the sense of writing a computer program, it's more in the sense of planning an operation. If you want to know more about the history, we recommend this publication. We're not going to really be talking about history in this class. We're mostly going to be talking about modern numerical optimization. How do we write the numerical optimization? I mentioned that we have a formulation, I mentioned a model. What are the elements of optimization? The elements are the variables. You can call them decision variables, degrees of freedom, parameters. They have different names. Nevertheless, they are the variables. So they are the things that you can change. Second, you need the objective function, the metric you want to minimize or you want to maximize. Third, you need a mathematical model that describes your system. And fourth, you need restrictions, which maybe are not part of the model, but you still need them. So for instance, you can have bounds of variables, you can have other restrictions. What I would like to point out is that even the term model is not always used in the same fashion. So some people would say that the whole formulation is a model. I follow, in this course, a more narrow definition of the model. Basically, the model is what describes your system. Is, for the engineers among you, what you've been learning in your classes on heat and mass transfer, on thermodynamics, on process design. So you have been learning models there. We take the model and the additional restrictions of these two elements, and we put them together as constraints. I already mentioned that the objective function can be minimized or maximized. So for instance, we want to minimize cost or we want to maximize the return of investment. Since you can reformulate a maximization always to minimization and vice versa, we are going to stick to minimization. This is just convention, and it makes our life simpler to follow a convention. Those of you who have taken thermodynamics, you remember that heat and work always go into my system. And if it happens to go out, well, then it has a negative value. Same here. We minimize a function. If we want to get the maximum return of investment, we will minimize minus the return of investment. What do I want to say more? Objective function I already mentioned. Typically, an objective function will be an economic or a thermodynamic or technological measure. It can be many, many things. mathematical model, in the simplest case, is written as equality constraints, more specifically algebraic equality constraints. If the model is of a dynamic system, maybe the equality constraints will be dynamic constraints. And we're going to cover that in our course. You can have also more complicated models, but we're not going to talk about it a whole lot. The additional constraints are typically written as inequalities. I would even say typically linear inequalities. And they arise from technological limitations. They arise from our desire. So I don't want to spend more than so much money. They arise from our customers' needs, product requirements. So you need to meet at least 98% purity or something like that. I talked about what is an optimization problem, and I talked about you use a numerical solver to solve it. Always when you solve a problem, it's a good idea to know what you're solving for, what you're aiming to get. So let us ask the question, what defines the solution of an optimization problem? Let's try to answer it. I said that we have some variables, and when we minimize a function, we want not to only find the minimum value of the function, we also want to find the variables, the values of the variables that give me this minimal function. It can be one solution or multiple solutions, but we want at least one. Sometimes we want all of them. When we solve an optimization problem, it's not enough to minimize our desired objective function. We have to, of course, satisfy the model and the additional constraints. There is no good in finding a solution that has a perfect return of investment but violates the law. When is it good to use optimization? What is optimization really good at? Optimization is really good at finding compromises between opposing effects. For instance, I can increase efficiency by adding a huge amount of investment costs, but my boss will not like that. Where do we apply optimization? Optimization we apply throughout science and engineering. In particular, in process and energy systems engineering, we apply it all the time. For example, we apply it in my lab. In general, you can say that you can answer business decisions. I don't happen to do that a whole lot, but others do. So finding your optimal product portfolio, finding whether you should invest or not, how much you should invest. I like more design. So what do I mean by design? I mean finding a process that optimally produces my desired product, or even finding an optimal product, or maybe the process and the product together. Optimization is also applied in operation. Operation means, okay, now we have a plant. How do we adjust the remaining degrees of freedom? How do I turn the valves in my plant? How do I control for disturbances? I also like combine design and operation problems. I said that to write an optimization formulation, I need a model. Funnily enough, to write a good model, you need optimization. What people have done is, for parameter estimation, for design of experiments, for model structure discrimination, they have formulated optimization problems that give you the optimal model, if you will. We are going to talk about this parameter estimation. We're not really going to talk about the rest. To make things a little more specific, I give you a few examples. I already mentioned design and operation in engineering, and in a following short video, I will show you some actual examples of that. Another prime example of optimization is operation research for airlines. Airlines face a lot of competition among them, so they have to be efficient. So they have to schedule their routes in a very clever way. And they do that by solving really big linear programs. They also have to decide how much you should pay for your ticket. And a very tricky question to ask is, should the pricing be such that the plane is always full? And maybe you have noticed when you fly that sometimes flights are overbooked, and sometimes they are overbooked and still there's empty seats. So they do quite a bit of tricky decisions. And a very nice study from MIT Sloan had shown that yes, it is indeed clever to not always have the plane full, so that you can accommodate a last-minute request who will pay a premium ticket price. You realize that when I start to talk about these things and I say maybe a last-minute request will come, you have to account for the stochastic nature. You have to account for the uncertainty. So the airlines cannot just write a deterministic model, they have to write a stochastic model. Or at least they have to have stochastics in their objective function and the constraints. I assume that you all have a cell phone that can tell you how to go from A to B in an optimal way. And what does optimal way means? Maybe shortest time, maybe shortest distance, maybe lowest fuel consumption. Maybe some of you have used LaTeX before. I love LaTeX and I really do not like Word. Although Word has improved over my lifetime tremendously, I still prefer LaTeX. Why is that? Maybe because I'm a nerd, but maybe also because LaTeX still produces documents that look nicer. And how does it do that? Apparently it does some optimization. Our Mother Nature has very many processes that are running, and we have described these processes by optimization. So if you think of evolution of species, the simplistic argument is that it's the survival of the fittest. So that's an optimization question. If you see behavior of many animals, they're optimizing their processes. If you think of my favorite thermodynamics, equilibrium processes are such that they maximize entropy generation. All of these things run in nature without numerical optimization. And maybe we're wrong, and it's not really an optimization process that we do, and our model of the nature is wrong, but this is our model of the nature. As I said, these are short examples, motivating examples. In another short video, I'm going to have more complete examples. At the end of each short video, I will be showing you such questions, and you should be able to answer these short questions on your own. If you're not able, it means you did not pay enough attention and you have to go back. If you are able, maybe it's still a good idea to revisit the lecture and also maybe read the written material we give you. If you're thinking of doing a PhD, or if you're already in a PhD, this is a fun cartoon I set up based on PhD comics. I stole the pictures from my favorite PhD comics, and I described back then as a graduate student how I felt PhD works. And now I have progressed from maybe being this guy to being this guy. But I still think there is a truth to my fun, or hopefully fun, slide. Thank you for the attention.